All right, last video of the unit is on energy in simple harmonic motion. We'll start with the pendulum this time and then talk about the spring. So for a pendulum and a spring, because the restoring forces are the spring force and gravity, they demonstrate conservation of energy. In other words, spring and gravity are conservative forces, and so there's an exchange in the oscillation of those two things of kinetic and potential energy. So we'll start with the pendulum. Pendulum obviously swings back and forth, but for this particular example, we're only going to focus on one swing. So essentially half of the period of motion of a pendulum from the moment you let it go to the moment it reaches the opposite extreme. And we assume like total energy conservation. So nothing's going to lose energy, even though in reality it always does. So, in our typical pattern, we would say, well, let's make this our zero potential energy line, because that's the lowest point the pendulum reaches, and so that's where gravitational potential energy is going to be zero. So starting at position 1, it's literally when you're holding the pendulum about to let it go, that is where the gravitational potential energy is at its maximum. That's kind of hard to see. And at the same time, the kinetic energy is equal to 0. So at the extreme here, nothing's happening. All of the energy is potential because the pendulum's at its highest point and the value of k is 0. Now, because the value of kinetic energy is 0, then the mechanical energy is equal to whatever this is. And then we let go. The pendulum starts to move downward, and so the gravitational potential energy decreases and the kinetic energy increases. That's position 2. Position 3 is special because we already labeled that as zero potential energy. So gravitational potential energy is equal to 0. And K is equal to its maximum value. Now these two values are equal to one another. So the maximum potential energy is equal to the maximum kinetic energy that it has. So that's an important relationship for conservation of momentum. By the time the pendulum gets to the bottom of its path, it has traded all of its gravitational potential energy for kinetic. Those two values are both equal to the mechanical energy of the pendulum. In position 4, it's on the way up. So gravitational potential energy is now increasing, kinetic energy is now decreasing. When it gets to position 5, it's essentially at position 1 again. Those are at the same height, and so we have the maximum gravitational potential energy and a kinetic energy of 0. So those are the important values in the oscillation of a pendulum. Now, once that happens, it then happens exactly in reverse. So it goes from 5 to 1 again, so you would go from here incrementally back up, and you just keep cycling back up and down. For a spring, we study a horizontal spring. And the reason we do that is because if we do orient the spring vertically, then we have to make complicated choices about the potential energy and elastic potential energy, the gravitational and the elastic potential energies of the spring. And we have to decide one location where both of those things are 0, and it actually depends on the spring where you can put that line. And you will end up not in trouble, but it's complicated. So in AP Physics 1, we stick to horizontally oriented springs only, which we can't really replicate well in the lab, but they exist. Okay, so the way this diagram works is it runs from top to bottom. This is the most compressed spring location, and then over here, this is the most stretched spring location. The x equals 0 is exactly in the middle. If I held onto the mass and let it either push or pull the spring, it would push or pull the spring until it got here. So this is equilibrium. And actually the same thing can be said of position 3 at the top. So the interplay in a spring is between kinetic energy and elastic potential energy. So in position 1, you have the maximum elastic potential energy because it's compressed as much as it's going to be compressed. And again, you have a kinetic energy of 0. And so this should look really familiar. The elastic potential energy as the spring decompresses, decreases, and the mass speeds up, so kinetic energy increases. At equilibrium, it has lost all of its elastic potential energy, and the kinetic energy is at its maximum value. After that, it's now starting to stretch the spring. So this is where the spring is kind of at rest. This is now stretched, and so the restoring force is pushing backwards. Now the spring potential energy is increasing, and it's slowing down. For step number 5, the maximum stretch, you again have the maximum spring potential energy and a kinetic energy of 0. So they're basically the same idea, but the overriding concept here is whenever you get away from equilibrium, the force is always pushing toward equilibrium. And so if it's moving away from equilibrium, it's slowing down and kinetic energy goes down. If it's moving toward equilibrium, it's speeding up and kinetic energy goes up. The other thing we're doing in this video is looking at graphs of energy. So we'll start with the same position versus time graph that we had in the previous graph video, and we'll say, okay, we started our maximum amplitude, and it goes to the bottom, and it comes back up to the top. So that's the oscillation that we're going to focus on for this. Now, to make a graph of kinetic energy versus time, we have to recognize that the kinetic energy can never be negative. And so 0 is the lowest possible location for kinetic energy. Kinetic energy is based on speed. So before you let go of the object that's oscillating, the speed is 0, and so is the kinetic energy. And so whenever the object gets to its amplitude, to its extreme, the kinetic energy becomes 0. So in this oscillation, there's actually 3 points where the object needs to stop moving, and so 3 points where the kinetic energy is 0. Based on what we did in the previous page, when the object gets to equilibrium, that's when it's moving its fastest, and so that's when it's going to have its maximum kinetic energy. But keep in mind, even though this is moving in a different direction than this one, they have the same value of kinetic energy because it's based on the speed squared. So we get this condensed graph for kinetic energy. This is very different from the graphs that you have seen in the kinematics world. And I just want to point out that for this right here, that's the mechanical energy. So at those points where you have maximum kinetic energy, it's when the kinetic energy equals the mechanical energy. And then at the bottom, we have potential energy. And so it's exactly the opposite. At the amplitude, before you let go of it, it has the maximum potential energy. Every time it reaches one of those maximum values of amplitude, that's when it has the maximum potential energy. Doesn't matter if it's a spring or a pendulum. When it gets to equilibrium, there's no more restoring force, and there's no energy being stored. And so we have the opposite graph. The graph of potential energy mirrors that of kinetic energy. The only thing about this graph is that it is capable of shifting up or down. You actually can have negative gravitational potential energy, and so in situations where there is gravity involved, you can get into a negative value. And then again, those maximum potential energy values are equal to the mechanical energy. So we'll do more with this in class, but those are the basics. Thanks.